So we just did a whole chapter on graphing, and that had to do with graphing linear functions, so there were no variables multiplied by each other. In this chapter, we're going to go over exponents and their properties, which are variables multiplied together. That's sort of where an exponent comes from. So things to remember before we get into this. This stuff is like the rules that are contained in this chapter are like the operations of the rules are very basic. Understanding them takes a little bit of thought, but like just learning the basic operations is very simple. So at the bare minimum, you should memorize these rules and memorize just the small operations that come along with them. Later on, we're going to be going over, I think I say this for every chapter, but this one especially so, we're going to be going over some real ugly stuff. And if you know your rules for your exponents, that stuff's not going to look ugly at all. It's just going to look fine. You're going to say, oh, I can simplify all that, no problem. But if you don't know your rules, man, it's going to look very intimidating. And of course, like always, having to slow down and re-remember the basic rules is gonna hold back your progress on more complicated problems. So, especially 4.1 and 4.2, there's a lot of rules that are easy to just memorize. Throw them on a note card, drill them. Okay, so powers and bases. So let's remember that when we're talking about exponents, this number down here on the bottom, this is known as the base. Well, this little number up here in the corner, this is known as the exponent. All right, so base, exponent. And remember, if we have an x to the third power, that just means x times x times x. All right, so remembering that definition, I'm going to introduce the concept of adding two exponential terms with like bases. So first we're going to consider x cubed, which is this one, x times x times x. Of course, x squared is just x times x. Now if we multiply these two together, x cubed and x squared, that's the same as just lining all these multiplications up together. So what you can see is when we multiply x cubed by x squared, it results in 5x's being multiplied together. We can ditch the parentheses on this next step, and we get a result of x to the fifth power. So see what we did there. We had x to the third and x to the second. That resulted in x to the 3 plus 2, which is x to the 5. So basically, we added those powers. We multiplied those together. So this is the official rule that relates to that, the product rule. So the product rule says that for any number for any number a and a positive integer n and m, a to the m times a to the n is equal to a to the m plus n. All right. So when we're multiplying together, x squared times x, let's say to the 7th, this is equal to x to the 2 plus 7, right? Which is equal to x to the 9th. Okay? And what you have to visualize here is two x's lined up, right? X squared is just equal to x times x multiplied by 7 x's lined up. See, this splits up into 7 powers of x. 1, 2, 3, 4, 5, 6, 7. If you count all these up, you get 9. And that's where this little exponent comes from. All right? So we're multiplying together. We add the exponents. All right, let's do some examples. So if we're multiplying 2 cubed and 2 to the 8th, this is equal to 2 to the 3 plus 8, right? 3 plus 8 is 11, so this is equal to the 2 to the 11th, right? All we did was we added 3 and 8. And this is, this is the 2 to the 11th is the product of these two. Yeah. Product, remember, product is the result of a multiplication, basically. Okay, so this one here, this is a pretty important example, and the reason for that is, right, the way this goes is we add up our exponents, right? But remember, this little 5 here has an exponent of 1. right? So don't forget to add that 1 in there. So this is 3 plus 8 plus 1. Yeah, 5 to the 12th. All right. So just because what we have, just because our bases aren't our normal single-term bases, that's not a big deal, right? Even if they're sums, this still works the same way. So with this, I can add, since these bases are exactly the same, I can just add my exponents. So r plus s, 6 plus 7, that equals 13. 7 plus 6, r plus s to the 13th. All right, and so even more complicated things, as long as the bases match, this works. All right, for this one. So since this is all lined up with multiplication, right? These are all multiplication. We can just drop the brackets, which means that we can rearrange my terms inside, right? And so I have an a cubed here and an a cubed here. I'm going to line those up. Then I have a b squared here and a b to the 5th here. I'm going to line those up as well. Okay, now I'm going to add my exponents. So I have a cubed and a cubed. That's going to give me a to the 6th. And then I have b to the 2nd and b to the 5th. So 2 plus 5, that's 7, b to the 7th. Any questions on those? No?
Would it be a 6 times b7?
Yes. Yeah, sorry, this is always multiplication in here.
It will equal just that?
That's it, yeah.
No one.
Yeah, they're not like bases or anything like that. Suppose I had a to the 4th times a to the 16th. What's my result going to be? Everybody think about it before.
To the 20?
Good. Okay, good. a to the 20th, right? a to the 4 plus 16, which is 20. Good. Okay, everybody think about this one before you say it out loud. What if I had a to the 3 and a to the 13th? Think about it. Hold that number in your head. Tessa, what do you got?
A to the 16th power.
a to the 16th. Good. We just add them. Okay? Yeah.
Because it's okay.
Yeah, and you just, you gotta visualize when you do this, right? This splits up into 3 factors of a right here, and this one splits up into 13, which I'm not going to draw them all out.
Okay, well, let me multiply those. We get a to the big number power.
If we multiplied what?
3
times 13. 3. Like we get pretty big.
Oh, yeah, you'd get 33, yeah.
And you're not going to draw 8 times 8 like 33 times.
No, I'm not. We are going to go over where we sort of do that, though, in I think it's in section 3. But for now, we're just adding them. All right, so that's what happens when you multiply 2 terms with like bases. Now let's talk about dividing powers with like bases. So the first demonstration here, you can see I divide a power of x to the 5th power and x to the 1st power, right? We are allowed to cancel 1 on the bottom and 1 on the top, and this results in x to the 4th. So this was, right, x to the 5 minus 1, x to the 4th. So this one too, x to the 5th up top, you can see I have 5 copies lined up. X to the 3rd on the bottom, I have 3. I can cancel 1, 2, 3 on the bottom, and 1, 2, 3 on the top. This results in x squared, which is equal to x to the 5th minus 3, if you'll notice. Gabe?
Can I say it again?
Sure. What?
Anything you cross out on the bottom has to be the same exact as you cross out on the top.
Good.
For instance, if you have xb and there's an x on the top, you cannot cross out the x before the b and then cross out the x on the top, because the xb and x are 2 different variables.
Oh, it has to be exactly the same.
Right.
Cancel. Okay. You can't just cancel it because you.
No, even though we want to sometimes. Okay, so that should inform us of the official quotient rule, which
was also on our quiz.
it was. Yeah, this is all.
Why didn't you give us this lecture before you handed us out that paper?
Because that's the point of the quiz, is to see if you guys took notes or not.
I think I did that one correctly.
Good. So this one basically says if you have some number a to the m over a to the n, that is equal to a to the m minus n, right?
Okay.
Just like this one right here, x to the 5th over x to the 3rd, that was equal to x to the 5 minus 3, which in the end was equal to x squared, okay? So when we multiply two together, we add the exponents. When we divide, we subtract. All right, here are some examples. So I have 7 to the 9th over 7 to the 4th. That's going to give me 7 to the 9 minus 4,
Is equal to 7 to the 5th.
which is equal to 7 to the 5th, exactly. All right, this next one, they're in parentheses, so the exponent applies to the entire term. So now I have 5a to the 12 minus 4, which gives me 5a to the 8th. Now, if I would have forgotten these parentheses on this last step, I would have been incorrect. 5a to the 8th is an incorrect answer to this. It's only correct when we have the parentheses there. All right, and so when you have an exponent outside of parentheses like this, leave it outside those parentheses unless you properly take care of them, which we'll deal with later. All right, but 5a to the 8th, this is not the same as 5a quantity to the 8th. All right. Okay, so let's do some more of these. This is a really common one. So for this one, when we have multiple different variables we're dealing with, I like to just split it up into sections and deal with it separately. So I'll deal with my my coefficients out here, 4 over 6. I can simplify that. What does that simplify into?
2 over 3.
2 over 3, right. Okay, so my p's, my variable that are p's, so that's p to the 5th over p to the 2nd. That means I'm going to have this as p to the 5 minus 2 up here. All right, for my q's, I have q to the 7th over q to the 1st. So that is q to the 7 minus 1. All right, so now this is 2/3 times p to the 5 minus 2. That gives us p to the third, q to the 7 minus 1. That gives us q to the 6th. All right, any questions on that one? Those ones are weird, but just remember, just keep going with the rule. You can split it up, and it works fine that way. Here's another one. This is another example of, because they're like bases, this rule still works. Even though we have all this other kind of junk in here, that doesn't matter. Since this base matches this base, the rule works. So this is t plus r minus 5 in parentheses to the 11 minus 8, which is equal to t plus r minus 5 in parentheses to the 3rd. All right, so next, 0 as an exponent. So let's just recall what we just went over, right? When you have something over something else, it's the exponents that are subtracted, right? And so this tells us that if we had some number a raised to the kth power, this would be equal to a to the kth power minus k, which is equal to a to the 0, because that's the rules of addition. We also know that any number over itself is equal to 1. So this tells us that any number a to the 0th power is equal to 1, right? It's equal to a to the k over a to the k, which is equal to 1. So this is our rule that we get from that. The official rule is the exponent 0, which says that for any number a, as long as a is not equal to 0, a to the 0 equals 1.
So in other words, 1 times 0, or no.
1 times 0 is 0.
But my head is hurting.
But 1 to the 0 is equal to 1.
Yeah.
Negative 1 to the 0 is equal to 1. X plus k plus 22 to the 0 is equal to 1. Doesn't really matter. It's always just equal to 1. The only one that you can't really do that with is 0 itself. 0 to the 0 is undefined. All right. So 1948 to the 0th power, what's that equal to? 1. Negative 9 to the 0th power, what's that equal to?
2.
3x to the 0th power, what's that equal to?
X.
No, it's 1. It's always 1. Whenever you got this 0 up here, it's always 1. Right? Even if what's in the parentheses was negative, even if this was negative 3x, it'd still be equal to positive 1. Now this one, this is different though. Notice I don't have the parentheses in this. And so the 0 doesn't apply to the 3 and the x together. It only applies to the x because that's all it's attached to. Right? The parentheses in this one meant that the 0 applied to everything in the parentheses. There's no parentheses here, so this is just 3 times 1, which is 3. All right, so parentheses matter a lot, especially with exponents.
So I have a question.
What's up, Gabe?
You don't really have to answer this right now.
Okay.
But are we able to prove that the 3x to the 0 exponent is actually equal to 1?
Are we able to prove this one or what?
Any of them. Are we able to prove that any number with the exponent of 0 is
Yeah.
indefinitely equal to 1?
Yeah.
All right.
And the proof goes roughly, like this is a very non-rigorous argument of why that's so. This very first one that I did. It's very non-rigorous though. A proof is far more structured than that, but that's roughly how it goes. You say like, yeah, these are established rules that we've already proven. We're going to use these rules to show that it doesn't really matter what the number is. As long as it's not 0, we get a to the 0 equals 1. And basically we say, we said, look, we showed with our rules that a to the 0 is equal to a to the k over a to the k. And we already know, because of math, that a to the k over a to the k is equal to 1. And so with that dual equality, we've shown that a to the 0 is equal to 1. To get into the weeds a little bit there with you guys. Sorry. Thanks, Gabe, for getting in the weeds on that one.
I told you didn't have to answer.
No, that was excellent. When we were talking earlier about deep thought, that's exactly what I'm looking for. I just like to tease you a little bit and give you some guff. Because you tease me as well. All right, so this is another important example, right? The 0 is attached to the 9, but clearly the 1's partitioned off by brackets. I mean, honestly, even if it wasn't partitioned off by brackets, this would be the same. So the negative 1 is not affected by the 0, so the negative 1 stays, and the 9 to the 0 just turns into 1. So this whole thing results in negative 1. All right, so now we're going to consider what it means to raise a power to another power. So what I mean by that is, suppose we have like an x to the 3rd. Sometimes we take that x to the 3rd and we raise it to like a 5th power or something like that. So there's specific rules on how to deal with that. All right, so let's consider first the definition of exponents. Y squared, of course, equals y times y, which gives us y squared. Y squared squared, though, that gives us y squared times y squared. If we break it up into its base elements, that is 4 copies of y lined up together, which gives us y to the 4th. Right? Notice that 4 is equal to 2 times 2. Now, if we have y squared in parentheses, I don't know why I just drew a u around the whole thing. If we have y squared in parentheses to the 3rd, that means we have y squared multiplied together 3 times instead of 2. So if we use our typical rules of multiplication with exponents, we know that y squared times y squared times y squared is equal to y to the 2 plus 2 plus 2, which equals 6. All right, notice that 6 is 2 times 3. The same thing happens when you take y squared to the 4th power. We get 4 copies of y squared lined up, which ends up giving us y to the 8th if we use our addition rule. What's up, Gabe?
So in other words, y to the 9th raised to the 8th power is y to the 17th.
Yes.
All right. So basically, we just take the number of the first power and multiply it by the second power if it's raised.
Yeah, you just multiply them together. Yeah, it doesn't really matter which, first power, second power. M times m, n is the same thing as n times m. Yeah, so this is your official power rule, right? It just says that when you're taking a power to another power, you multiply the exponents, right? And so these are those simple rules. You guys can see that they're all very similar but slightly different. And so this is why you should memorize these. Okay, so when we have x cubed times x squared, right, we add these. When we have x cubed taken to a squared, we multiply. All right, let's do some examples. So m squared to the 5th power, right? If I wanted to write this out, this would be 5 copies of m squared multiplied together, but I don't want to write it out. So I'm just going to follow the rule. I have m to the 2 times 5, which gives me m to the 10th. Precisely. Okay.
The other examples.
Yeah, where were the other examples? I don't know. Okay. I guess there were none for that. Okay. This is a good one here. This is important. So this is kind of what we were getting at with how important the parentheses are earlier. This is raising a product or quotient to a power. So you can see with this example here, these are in parentheses, which is why it's lined up 3a times 3a times 3a. Now, if this weren't in parentheses, here, I'll do this on the other side. Suppose the 3 were not in parentheses, was not in parentheses, and I had 3a cubed, right? The cube only applies to the a. So that would there'd be nothing else to do with this. I'd just have 3a. Whereas this one turns out to be 3 cubed times 3a. Basically, what this rule says, raising a product to a power, this rule says that you have to, in a sense, distribute this exponent into each term in the product. All right, and so if I have x, y to the 3rd, this is equal to x to the 3rd, y to the 3rd. If I have 2y to the 99th, this is equal to 2 to the 99th times y to the 99th. All right, I sort of distribute into every single term inside the parentheses. All right, if I have multiple terms lined up, if I have 2xyz to the 3rd, then I have 2 to the 3rd, x to the 3rd, y to the 3rd, z to the 3rd. All right? So let's do some examples. So I have 4a cubed. This gives me, when I distribute, this gives me 4 cubed a cubed. All right, I don't know. I suppose we could do the math on the exponents or on the coefficients. So this is 64 a cubed. Typically, in your answers in the book, I'll ask you to, just do the math on like these kind of things where you can actually do it. Okay, so this is a good example here. So for this one, remember, we have to distribute the 2 in here. So this ends up being -5 squared x to the 4th squared. -5 squared is equal to +25. And then x to the 4th squared, I multiply those, so I get x to the 8th. Alrighty, so with this one, we just noticed real quick that we've got an exponent outside of these, which means we have to distribute that before we work with anything in here. So I'm going to distribute the exponent of 2 in. So I'm going to have a to the 7 times 2, 7 times 2, b b had a little 1 exponent up there, even though we didn't expressly draw it, but there's a secret little 1 up there, so that means this is 1 times 2. And then the other parentheses can just stay as they are, a cubed, b to the 4th. So on my next step, I'm just going to do the math in each of these little exponents, and I'm going to rearrange everything so it's right next to each other. So I have my a and my a. 7 times 2 is 14, so I have a to the 14th times a to the 3rd. And then I have b to the 1 times 2, which is 2, and b to the 4th. All right, so now, for my final step, I got to add all my exponents up. So I get a to the 17, good, b to the 6th. All right, any questions on those? Okay. All right, so the next rule we're going to go over is the raising a quotient to a power rule. This is roughly the same as raising a product to a power. It basically says when you have an exponent outside of a fraction, you distribute that exponent into the top and the bottom. If you've got multiple terms in the top and the bottom, you distribute to all those terms. For example, this is something confusing you may see if you have xy over, let's say, 2, and that is taken to the 3rd power. Right, the 3's got to distribute into the numerator and the denominator, so it hits every term in each of those, right? Every factor. So we have x cubed, y cubed over 2 cubed. That's what that would be. Okay?
So would that equal 1?
What, this here?
Yeah.
No. Depending on what x and y are. For some values of x and y, yeah, sure. But for most, no.
So it's not xy over 2 times xy over 2 times xy over 2 because there's a parenthesis.
That xy over 2 times that is what it is, right? And so
Oh, that's how you write it down.
yeah, and so like that's
Okay, I see.
yeah, you can totally write this as 3 fractions, xy over 2, xy over 2. Yeah, exactly. It's the same exact thing. Because the rules of multiplication, when it comes to fractions, we just multiply straight across the top of all these and straight across the bottom, right? Yeah, which would give me 3 copies of x, and then 3 copies of 2, and 3 copies of y. Whoops, that doesn't,
Whoa.
that makes everything look bad. Anyway, you guys know where the y's are, right?
Yeah.
Oh no! I broke it.
Because it's like, why are you using all these colors?
Right? All right, let's just, now I have to hook up my keyboard.
Red is real.
All right.
But cool. That's the quotient power.
Yeah, that would be
Okay.
the quotient.
Here, it's like,
There we go.
there you go. I guess I didn't like
All right.
that either.
And I'll just scroll that little demo out of the way. All right, so how to use this. If they ask you to simplify something like this, you just distribute it in there, right? So the 2 applies to the x, and to the 5, we have x squared over 5 squared.
But anyway.
It is 25, yeah. All right, and so the same thing happens for this guy, part B, right? So we'll have 5 cubed on top, and we'll have a to the 4th taken to the 3rd power on the bottom. So 5 cubed is 5 times 5, which is 25, times 5, which is 125.
Okay, that's 120.
And then a to the 4th raised to the 3rd power, what's that? Which rule are we using there?
4 times 3 is 12.
There you go.
8 to the 12.
Yeah, we were raising a power to another power, so we multiplied. All right, a to the 4 times 3 is a to the 12th. Good. Okay, one more here. So I'm going to distribute the 2 into the numerator. I'm going to go ahead and throw some parentheses around that numerator just so that I keep everything straight. And same thing with the denominator, b cubed taken to the second power. Okay, now in this next step, I'm going to go ahead and distribute the 2 into the numerator. So I have 3 squared, a to the 4th squared. In the denominator, I have b cubed taken to the second power. What does that equal?
B to the 6th power.
6th power, right? Yeah, because we multiply these two guys. It's a power taken to another power. So b to the 6th. All right, my next step, 3 squared, that's equal to 9. A to the 4th taken to the second power.
A to the 8th power.
Yeah, a to the 8th over b to the 6th. And that's it. That's my final answer.
Yay.
All right, so if you want a summary of these rules, a decent one is on page 235. It's pretty easy to go through the chapter, though, and sort of pick these out. I already said it once, but yeah, you want to write these down somewhere before you do your homework. I mean, even if you're not going to memorize them, write them down on a piece of paper and set them right next to you when you do your homework so that you don't have to keep shuffling back in the chapter for the formulas. That sucks. Like, just put them on a paper, put them next to you. Then you can do your work quickly. All right. Any questions about the rules of exponents?
Yes. Can you go back to the first one? Because I kind of missed the example for the first one.
The first what?
Column A, the tab A.
Oh, since you were late to class, no. That was a good try, though. Okay. He's just like, could you maybe just go over the first 5 minutes? I didn't quite understand that.
I just wanted to see what the example is.
Oh, okay.
I was like, what if I needed a review?
The examples were all pretty basic. Yeah. Watch the video later. Get to class on time, Gabe. So funny. Yeah. As long as it's not like a live feed from the university.
Oh, did you do that too? Oh.
Okay, so let's go into the next section. So we just learned about positive exponents, right? And a positive exponent is this. It tells you how many copies of x are multiplied together. Now, in this chapter, we're going to go over what it means to be a negative exponent.
So I don't like negatives.
A lot of people do not like negative exponents. If you want to alleviate that, memorize these rules. Negative exponents are a lot friendlier when you know the rules. All right, so we know what x cubed means. Now let's think about what x to the negative 3 means. So if we start with x to the negative 3, and we know that it's over 1, we can multiply that by x to the positive 3. And I'm just going through these to show you why we do this rule, right? This isn't something you guys will do in a problem. So we can multiply by 1, or in other words, we can multiply by x cubed over x cubed. Using our normal rules for addition, this gives us x to the 3 minus 3 in the numerator and a plain old x to the 3 in the denominator. Right? When we do this addition, we end up with x to the 0 in the numerator, and the x to the 3 remains in the denominator. X to the 0 we know is equal to 1, so as a final result, we get 1 over x cubed. So we started with, and maybe I should write our actual here. This is what we started with. It's a little confusing to look at all that. This is what we started with, x to the negative 3. And we turn that into 1 over x cubed. Yeah, Tessa?
So we're on 4.2, right? Polynomials?
Yeah.
My book is not saying those things.
Which book do you have?
It says terms, protect polynomials from coefficients. It doesn't say negative.
What book are you using?
This one. Scientific.
Oh, okay. Oh, they rearranged the chapter, didn't they? So you might be looking at 4.8 then. Take a look at 4.8 if you have the old book.
You can borrow my book.
No, it should be all in there.
Oh.
If you have the old book, it's 4.8. If you have the new book, it's 4.2. Yeah, I think it's 4.8. Is that it? Yeah, there you go. Okay, sorry about that, guys. Yeah, that's a little bit confusing. So we found another difference in the book.
More than you thought.
Yeah, I know, right? If you guys are watching the lecture at home, you've been warned. If you don't know about that next week, I guess we'll know that none of you guys actually watched the lecture. Okay, thanks, Tessa, for pointing that out.
See it on the homework.
Right? Well, that's just it. And so, your homework for tonight, does anybody have the homework schedule for tonight?
Yeah.
Does it say 4.8 on it?
4.2.
Okay, good. Okay,
4.2.
good. Excellent. So I fixed that part. All right. Yeah. If you have the old books, your homework's just going to come out of 4.8. So do your homework problems from 4.8, not 4.2. Hopefully that doesn't cause too much confusion. That's what we get for using two different generations of book. It's cheaper that way, though. What the heck was that? All right. Where were we? Right? Start the class again, dork. All right. So that brings us to our official rule for negative exponents. Basically, if you have a to the negative n, you make that n positive by throwing it underneath the fraction symbol, to the other side of the fraction symbol, I should say. Right, and so this is the sort of counterpart of that rule, right? And this may be a little obvious, but, whoops. So the counterpart of that rule is 1 over a to the negative n is equal to a to the positive n.
Yay.
All right, so here is an example we might see for that rule. And this says, express this using positive exponents and simplify if possible. Well, following the rule, this says any a to the negative n is equal to 1 over a to the n. So this is just 1 over m to the positive third. Don't forget to switch the sign on your exponent, right? This goes from a negative to a positive.
Yeah.
All right, 4 to the negative 2, this is 1 over 4 to the positive 2, which is 1 over 16. All right, so this guy, negative 3, we have everything in parentheses, so we're going to leave it that way. 1 over negative 3, this negative 2 turns into a positive 2 since I flipped it to the denominator. All right, negative 3 squared, that is positive 9.
I was gonna do like reciprocal.
Yeah, exactly, yeah.
Just a bunch of them.
So, okay, here's a good one, right? So notice, I'm not sure if this was supposed to be the example or if I just put the parentheses in the wrong place, but notice the parentheses are on the outside, which means that the negative 1 is only attached to the b and not to the a, right? So we can flip the b, but the a has to stay there. Okay, this is an important example. This is going to come up a lot. So the a just stays, and that's right, the b goes to the bottom, and that's it. Right? Yeah. So negative 1 is attached to the b, but not to the a.
Yeah.
But if things were a little different, if it was ab to the negative 1, and these were in parentheses, this would equal
Attached to both.
1 over, right, a, b. Okay, so that's the big difference there.
Yeah.
All right, when we have negatives in the numerator and the denominator, it works to just flip the whole thing, right? So this turns into b to the positive 3, a to the positive 2, right? I just flipped them over and turned the exponents into positives. All right, how would I express this guy in terms of a negative exponent?
X to the negative 7.
Good.
Yeah.
Right? You flip it and throw a negative sign on the exponent.
Or would it be x over x to the negative 7 over 1?
Would it be what?
What would be x to the negative 7 at the top?
Yeah, it already is.
I know.
All right. So if we are multiplying these guys like usual, it works. You use the normal addition rule for multiplying positive and negative exponents, right? So t times t to the negative 2, this is equal to t to the 5 plus a negative 2, which is just t to the 5 minus 2, which is equal to t to the 3. I'll show you why that's true. So t to the, whoops, that's not a t. T to the 5 times t to the negative 2, this is equal to t to the 5 over t to the positive 2, and then we can just use our normal rules of exponents. If your head's spinning a little bit, don't worry. Once you memorize all these rules, this stuff will go a lot smoother. All right, so this guy. And you guys will find, I mean, when you're dealing with negative exponents, just use the normal rules, right? You use the same rules of taking a power to another power with negatives as you do with positives. All right, so this one, to get rid of these parentheses, I'm going to distribute the 4 into each and every term. So I distribute it into the 5, and I get 5 to the 4th. Distribute it into the x squared, and I get x to the 2 times 4, which is 8, right? Because this is taking a power to another power. Then I get y to the negative 3rd to the 4th power. We'll do that on the next step. So I have 5 to the 4th, which is, I don't know, 625. X to the 8th, that stays the same. And then this y to the negative 3 times 4, right? This is multiplication because I'm raising a power to another power. The result is negative y to the negative 12, just like it would be if you multiplied those two numbers together. All right, and so in the end, because I don't like negative exponents, I want to fix that. So the final answer to this will be 625 times x to the 8th over y to the 12th. What's up, Bella?
How do you tell that 5, it's not 5x to the second term? There's 5, it's 5, and then there's x to the second term?
Good question.
It looks like they're together.
Because there's no parentheses around them, right? If those were together, this would be written like this, 5x squared y to the negative 3, right? The parentheses are what groups the terms in multiplication, especially like when it comes to exponents. And so because there's no parenthesis, the square only is attached to what it's attached to, nothing else. Same thing with this negative 3. If there was anything on this 5, the same thing would be the case. Does that answer your question?
Yeah.
Okay, good. Okay, so with these ones, you can do this two ways. You can do it using the strict addition rule, and so I'll just flip them first. That'll make more sense. So since they're both negatives, we can flip them to turn them positive. So the x to the negative 5 turns into x to the positive 5, but it goes on top. And then the x to the negative 4 turns into a positive 4, but it goes on the bottom. And then we use the classic addition, or the classic quotient rule. So this is x to the 5 minus 4, which is just equal to x to the 1. So if you didn't want to do this middle step, though, you know, you could use the addition rule also. So this is just an alternate way to do the same problem, and you would get x to the negative 4 minus a negative 5, which would give you x to the negative 4 plus 5, which is x to the positive 1. So it's the same answer, just two different ways to get there, both equally valid. All right, here's another one. Write this guy without negative exponents. I just flip it to the top. T. Nice. All right. This guy here, they're not like bases, so we can't cancel them. We can't use the traditional addition rule, so we just flip them to make their exponents positive and call it a day. So t to the positive 5 over s to the positive 3. Ooh, this is a pretty one. All right, so on this one, once again, I like to just consider it all separate, right? I do the numbers first, the x is second, the y is third. So negative 10 over 5, negative 2 over 1, exactly. All right, x to the negative 3 times x cubed, or x, no, sorry, x to the negative 3 over x squared, excuse me. I'm just going to flip this negative exponent to the denominator. So I have x squared times x to the positive 3 now. Okay, now I'm going to deal with these y's. No, this is a weird one. The negative 2 comes because I have negative 10 over 5.
Which is equivalent to negative.
Yeah, so I simplified that guy to negative 2. So on this, to deal with the y's, I'm just going to sort of brute force it in a way. I'm going to use the regular quotient rule. So I have y on the top, and it's to the 1 minus 5. Any questions on that, what I just did? Okay, you guys look confident. All right, so now I have negative 2 still. I have x to the 5th in the denominator, because that was 2 plus 3. Then I have y to the 1 minus 5 in the numerator, y to the negative 4. I don't like positive exponents, so I'm going to rewrite it on the last line in a better form. So I have negative 2 in the numerator, and then x to the 5th, y to the positive 4th in the denominator. So with these, it helps to do these by baby steps. One of the biggest mistakes you can make is trying to do multiple steps in one line with these, because when you go back and you look at your work, you can't tell what you did. And so, even if it's tedious to say, okay, on this line, I'm only going to do 2 things. I'm going to move the x down, move the y up. It helps to just go one little step at a time when it comes to these, till you get really used to them. All right, so as we basically showed in the previous examples, when you have 2 exponentials with non-like bases and they have negative exponents, you can, oops, darn it, I always do that. Don't write that down. You can flip them and make those exponents positive. So this is b to the positive and a to the positive m. All right, let's go over one such example. So for my coefficients, I have negative 15 over 5. That is negative 3, right? Okay, so this is equal to negative 3 so far. I know that's true. Maybe we'll handle the x's next. So x to the negative 7, I'm going to flip that to the bottom. That's going to turn into a positive 7. We have y squared in the denominator. That's not a negative exponent, so we really don't have to do anything with the y squared. It just stays there. That's fine the way it is. And then we have z to the negative 4th. We want to make that negative 4 positive, so we flip the whole thing to the top. Z to the positive 4. And that's it. All right. The previous rule basically leads to this almost directly. If you have some fraction, a over b, and it has a negative exponent, and the whole thing has parentheses around it, you can flip the inner fraction, and that turns the exponent positive. So 2/3 to the -2 is equal to 3/2 to the +2. All right? Just flip it. All right, so suppose they want us to simplify this guy. We can we could do this two ways. We could distribute into the top and the bottom with this -3 and then flip all the terms later. Or, since we just learned our new rule, we're going to flip it right off the bat. So I can rewrite this as 2y over x to the 4th to the +3. All right, now I go ahead and distribute all this. So it's 2 cubed y cubed over x to the 4th cubed. Right, 2 cubed, that's equal to 8. Y cubed, that's equal to y cubed. And x to the 4th raised to the 3rd power. Since we're raising a power to another power, what is it?
X to the 12th.
X to the 12th, good. Yeah, we're multiplying them. All right. Okay, so that is negative exponents. Any questions on those? All right, just remember, when you do your homework for these chapters, write down all these rules and keep them right next to you. Right? Don't waste your time by searching through pages. All right, let's talk about scientific notation. All right, so scientific notation, it's really just like it's a very efficient manner of putting huge numbers into a small space. And so the mass of the Earth, this is a massive number. You can see, like, we would write 24 zeros on it. If we wrote it out the longhand way, we can compact it into this simple scientific notation piece. We write it out in scientific notation. Same thing goes for the mass of a hydrogen atom. Yeah, you can see it's just a very tiny number put into an efficient form. What's up, Gabe?
My favorite thing about the scientific notation is that if you have a bunch of numbers before you hit 0, the times 10 to the 24 only counts how many zeros are in it. Everything else, like if you have like a 6.54321, and then you had a bunch of zeros after it, you would write it as 6.54321 or 65431, and then you count how many zeros are after that and put that as times 10 to that power.
But it would be 6 point. So there's more rules that come along with that. But yeah.
Oh, I see.
So.
Wait, do you count the zeros after that too, or just
After
the zeros?
you have all the numbers before the zeros inside this inside that decimal form.
Let's go. Let's do the official. Let's do the official rules. That's he's on it though. He's got.
I should probably learn this first before.
All right, guys. So just remember, numbers with negative exponents. So like this guy here, that represents a very small number. Numbers with positive exponents, that represents large numbers. Okay. So this is the way scientific notation always works. It has an n, a number right here, times a power of 10. The specifics for the n is that it's got to be greater than or equal to 1 and less than 10. Right? And so that's how you know where to put your decimal. Right? If you have some number like, whoops, wrong pen, 6,324 or something like that, and they said put this into scientific notation, you wouldn't use 63.24 as n, because that's way bigger than 10. You wouldn't use 632. You would have to use 6.324, because that's the number that's in between 1 and 10. So that's what n has to be. If n is like 23, that's the wrong number. You got to adjust. You got to adjust your scientific notation.
Would the scientific notation be 6.324 times 10 to the 1?
No, it would actually be times 10 to the 3.
Oh, right.
And that's because, yeah, it's not the number of zeros, it's the number of decimal places. Yeah. Okay, and so, basically the way that scientific notation works, if you're going from scientific to decimal form, is you start with any number, we'll just call it 3.0 for now, and if this number is times 10 to a positive integer, let's say it's 3, right, then you take your decimal on your n and you move it 3 places over to the right, making this a larger number. So this is equal to 3 times, right, 1, 2, 3, 3,000. Okay, but if we have 3.0 times 10 to the negative 3, the decimal moves the other direction 3 times. All right, and so we would say 3.0, 1, 2, 3. This is where the new decimal point is. So this is equal to 0.003. Okay?
Would that be the thousands?
Yes. 3,000, 3,000 thousandths.
I hate it when that's probably my least favorite thing about it is they put the P just
Thousandths.
trillions.
Okay, so if we're asked to convert these guys to decimal form, we just have to look at whether the exponent's positive or negative and move the decimal place accordingly. So this is a positive decimal, or a positive exponent, which means this is a large number. So we move the decimal place exactly this many times to the right. So I have 1, 2, 3, 4, 5. So I put 2 extra zeros in there basically. So this is 7, 8, 9, 3, 0, 0. 789,300. All right. So with this example, we're doing the opposite, right? And so maybe it'll help me to organize my work if I just write my 4.7 way over here. All right, so I have to go, this is a negative exponent, so that means I have to move the decimal 8 times in the left direction. This represents a small number. So I say 1, 2, 3, 4, 5, 6, 7, 8. So let me write this out a little more properly. So decimal 1, 2, 3, 4, and then 4, right? Yeah, 4, 7. All right. So that's the decimal form, right? And notice there's actually only 7 zeros, and that's because one of my movements took up the 4 place. All right. So just remember, sorry about all this. So if it's a negative exponent, we move the decimal to the left. If it's positive, we move it to the right. Yeah, suppose they went the other direction. So first of all, what's my n going to be for this number? Remember what n has to be. N's got to be between 1 and 10, right? So what's my n going to be? 8.3. 8.3. Good, good. So what I need to do is I'm going to notice where my decimal is now, and I'm going to count how many times it needs to jump to reach, to create n, basically. 1, 2, 3, 4, right? So this is equal to 8.3, whoops, 8.3 times 10 to the 4th, right? I know that the positive exponent is the right one because 83,000 is a large number, right? So this scientific notation should have a positive exponent. If it was a really small number, it should be negative. What's up, Gabe?
That really small number up there is 47 billion.
There you go. Okay, so now let's play this game with a small number. All right, so what's my n going to be?
3.27.
3.27, right? Yeah, because that's in between 1 and 10. Okay, so I just play this game again. I notice where my decimal is, and I count how many times I need to move it over. So I need to move it over 2 times. So I have 3.27 times 10 to the negative 2.
Oh, right.
Right? Move it over twice.
To get to the 3. So
Gabe, you gotta slow down. Slow down.
This is why I always try to do it on time.
Yeah. Okay, any questions about those?
It would be a small number.
Yep.
So, yeah, so negative exponents, smaller numbers. Positive exponents go to large numbers. Yeah. Okay, so let's go to how to mess with these, how to work equations with these, and how to do operations. So just remember, if you're at a loss for how to do scientific notation operations on an exam, you just need to follow all the rules for normal multiplication and division with exponents. That's all you need to do, right? That's all we're doing here. So when I multiply these two together, I just split them up into terms that make sense to combine. So I have 2.3 and 1.8. So I combine those. I say 1.8 times 2.3. And then the other part is the exponents, right? So I have 10 to the 9th times 10 to the negative 4th. All right, so 1.8 times 2.3, that gives me 4.14. And then I have 10 to the 9th times 10 to the 4th. So by the rules of exponents, 10 to the 9th times 10 to the 4th is just equal to 10 to the 9 plus 4 plus negative 4, which is 9 minus 4. So that gives me 10 to the 5th, right? Okay, so this is 4.14 times 10 to the positive 5th. And really, like, we kind of treated that as if this were just a variable. That's basically kind of what we did there. We just split it up, like, you know, as if the base 10 was actually like an x or something like that. We just never computed it, left it the way it was. Okay, so what about dividing these guys? So here's that pesky little division symbol that we're going to get rid of soon. But we're still using it in this chapter for whatever reason. So just like with the multiplication, we do this the same way, right? We keep the coefficients together and we keep the powers of 10 together. So this is 3.41 over 1.1. And we have 10 to the 5th over 10 to the negative 3rd. All right, so I do the math on the coefficients. 3.41 divided by 1.1, and I get 3.1. And then with my exponents, I notice that I have a negative, so I can flip that to the top. So this is times 10 to the 5 minus, hold on. Let me write that a different way. And so this is 3.1 times 10 to the 5th times 10 to the positive 3rd, because I flipped that negative 3rd up to the top. All right? Not to the 2. Right? These are both positive, and we're multiplying like bases, so we add them.
Oh, 8.
Yeah. There you go. So that's my final answer.
Wait, how did you get 3.1?
3.1. 3.41
Oh, yeah.
divided by 1.1.
Yeah, if you just do that on your calculator, you'll get 3.1. And so I really do split them up. And so I take this part and this part, and I divide them completely
You
separately.
just divide them and
Yeah.
you got 3.1. Okay.
And then I take this part, and I do those separately. And then in the end, you put it back together.
A trick that works for me, but not all the time, because I sometimes get the wrong answer, is if it's 3.41 or like for the 3.41 and the 1.1, the new is going to be like shame on you for this. But I noticed that there's a 1 and a 1 on it, so I just cross out the 4. And then I take the top
Oh, like,
one. See, he's already doing it. He's already doing it.
wait.
I don't know about that technique. I don't know.
Don't do it. It doesn't work for me.
Oh.
That's the thing about math, though, right? We don't do things that only work part of the time, right? We do things that work all the time if they're in the right situation, right?
Probably their math teacher.
It's so funny. That sounded like an interesting technique. I would like to hear about that later,
That
Cam.
work
All right.
all the time. Not this one.
Okay, so for this one, once again, I'm going to collect the terms that go together, right? So the coefficients, 3.1, and this is multiplied by 4.5. And then I'm going to have 10 to the 5th multiplied by 10 to the negative 3rd. So, what'd you get? 13.5?
Oh, I could be. Oh, yep. Wait.
Okay.
Oh, there was 13.95, I think.
Yeah.
For the first
I was close.
Excuse me.
one. And then you
So
said,
13.95 is what we get when we multiply those coefficients. And then what do we get when we combine our powers of 10? Good, 10 to the 2nd power, right? Because when we're multiplying together like we are up here, we add the exponents, right? And so 5 plus a negative 3 equals 2. So we do have one problem, though. What's my problem? Yeah, 13 doesn't work. That's not our n. We have to adjust this one. So now, yeah, we want this to be 1.395 because it's got to be in between 1 and 10. So, well, yes, exactly. We just move the decimal one more time and add an extra power on, right? And so this is a larger number. We're going to move this over once. This is going to equal 1.395 times 10 to the 3rd.
but 5 plus negative 3 is not 3.
Yeah. So what he's saying is that when we multiplied 3.1 and the times 4.5, because we got a 13.95 and 13 is bigger than 10, it can't work. So we have to do the decimal over to 1. And
So-
then we get a smaller.
We landed, so
You're too smart.
we landed on this number, and you're absolutely
I
correct.
can still see. Anyway, so I get what you're saying.
So,
Just forget the.
here, this will make it harder. So we landed on this line, right? And you're exactly right. We had 10 to the 2. But then we noticed that this was wrong, and we
Yeah.
needed to adjust a little bit. We needed to move this decimal point one more over here.
Okay.
And to do that, we had to increase this exponent by 1.
Oh, okay.
Okay.
It doesn't matter if 10 third is equal to 10 fifth times 10 to the negative. third.
Yeah, that's
Because
all we
it's
did.
already done in
This is
okay.
correct, and then we just adjusted it one more
Yeah,
time.
'cause-
Yeah.
Okay. That has to be just cool.
Okay, so
I did not explain that.
all right, so
So that's what you meant. Oh.
so we're almost done here. So let me just show you how I'd set this one up real quick. So to set this guy up, notice we have a division here. We would say 7.2 times 10 to the negative 7th over 8.0 times 10 to the 6th. And then we just separate these just like I did before and sort of handle them separately. And so I do 7.2 divided by 8, which would give me 0.9. And then I do the math on these guys here. And actually, maybe I'll just do the math on those because because you guys are always out of here early.
Is negative
Um,
negative 7 plus 6?
Negative 1.
so it would actually be negative. So, and this is weird because we're used to getting rid of the negative exponents. But when we're using scientific notation, the negative exponents are just fine. So that's actually what we want. We want to simplify the numerator. So we have 10 to the negative 7th, and then we have 10 to the 6th on the bottom. So I have negative 7. I'm going to flip this 10 to the positive 6 up. That's going to turn into 10 to the negative 6. So then I'm going to combine those. So I have 0.9 times 10 to the negative 7 plus negative 6 equals 10 to the negative 13. Exactly. But, Bella, sorry, that's scary. So, but our n is not what we want it to be, right? We want our n to be 9 instead of 0.9. So,
9.0
yeah, so we take
to the negative 12. Or times 10 to the negative 12.
But isn't 0.9 what was that time?
negative 14.
But it's less than 1.
Oh, it's less
Exactly,
than 1.
between 1 and 10.
Oh,
Yeah.
I forget it's less than. Oh, okay.
So why would it be 14?
Because we went one further in the negative direction, right? Yeah. We made something smaller, larger, sort of. It's weird if you, don't overthink it, because if you overthink these, they get really confusing. Okay, one more thing before you guys leave. So because I allow calculators on all exams, and you can completely do all these scientific notation problems and check your work with calculators, I demand that you show me those mid-steps. Demand it. So I don't care if you use calculators to check your work on exams, but I want to see like this middle step where you're adding the exponents. You have to go through great pains to show me that you know the concepts, all right? So yeah, I'm super rough on people who just give me an answer in scientific notation. Like, you had your calculator, why is this important to just write the answer? Show me the steps. So that's it. Sorry for taking up a few extra minutes, guys.